All right.
So again, this is going to be an abbreviated lecture over chapters 5 through 8, and talk a little bit about what chapter 9 entails, which really Trina's going to go over in depth this semester. But it does have a part in our technique selection and why we set techniques the way we do. So we're going to touch on chapter 9 as well. So X-ray creation, interaction with matter is where we are for, I think got two mice up here. All right, so the imaging system, if you remember, is identified as in two different ways, that is use and the energy created. And I'm going to be asking y'all, for some feedback on some of this stuff, see what you remember. What were examples of usage? Come on, y'all, second semester students, you should be comfortable with each other by now, so there's no reason for you not to speak up. What are examples of usage? What's that? You got diagnostic x-rays. What else? Okay, you got CT. CT is a little bit different, but you do have CT as far as different types of diagnostic x-rays. Diagnostic equipment, you got you got diagnostic and you've got mammography, right? You've also got diagnostic and you got fluoroscopy, would be differences in usage. Differences in energy would be like mammography versus diagnostic in your mammo machines. Your KVP selection is, the upper end of your KVP selection is going to be maybe 40 KVP. What do you use? What's the upper end of what you can set on your machine? 120. Some machines may even go up to 150. All right, so the characteristics of the couch, the table that you put the patient on. I always put the couch in quotations because couch seems like it's comfortable. Have y'all gotten on these things yet? Mm-hmm. Yeah, I hope so. Just to get a perspective of what your patient has to go through. So the couch has to be radiolucent. Not only does it have to be radiolucent, but it has to be uniform thickness. And why both of those? If it's radiolucent, why isn't that enough?
Because even if it's too thick on the part, it could still show a little bit.
Right, what is radiolucency? It goes through, but is it radioparent?
No.
And the answer is no, right? So radiolucency just means that it transmits most of the x-rays, but some of the x-rays would be absorbed. So even something that's radiolucent, if it's thicker in one place than the other, then it's going to give you an artifact. So both of those reduce the likelihood of artifacts. The principal parts would be the tube, the console, and the high voltage generation system will be your principal parts of your imaging system. So on the console, if you remember, we can control the quantity and the quality of the x-ray beam. So the quality is really how likely something is to penetrate. We'll talk about that in a second, but the intensity is your quantity. So when I was in school, I had a hard time making the leap between intensity and quality. Intensity to me meant power meant KVP. But in this context, intensity just means numbers. So intensity is the quantity, which is directly related to the mass that you use. You change your mass, you double your mass, you double the number of electrons that you collect in your thermonic emissions. You're boiling off the electrons, so you double those. And then therefore you double the number of electrons travel across the tube, and INSO you double the number of x-rays. So there's a direct relationship between that. But if you remember, KVP was directly related, but it was also exponential. So if we increased our KVP by 15%, what did we get in output? Especially post-patient. What happened to the number of X-ray photons incident on the image receptor. Double, right, so it's exponential. It goes in the same direction. You increase KVP and you increase the numbers, but you increase the numbers exponentially. All right, so the KVP, how we control it is just with KVP settings, and we tend to think of KVP as being what controls the quality, whereas really half-value layers better quality describes a better quality X-ray beam. So that if you have two X-ray beams that put out the same KVP in numbers, so you put out the same quality in KVP, you put out the same numbers in mass, and one absorbs, you put an absorber in both of them, and the absorbers are identical. And after the X-ray beam passes through those absorbers, one has more remnant beam, secondary beam, then that is a higher quality X-ray beam because it penetrated better than the other one, right? So half-value layer is a better measure. The higher the half-value layer, then the better the quality X-ray beam. But what else controls it would be generator type. If you're using a three-phase machine, if you remember back, we talked about single-phase and three-phase, and the difference between them is overlapping pulses, right? And with the overlapping pulses, we said our KVP never drops to 0, right? So in that way, we have a higher average X-ray beam, which gives us a higher half-value layer, even though the KVP is the same, okay? So generator type, three-phase generators and high-frequency generators have a higher quality than single-phase, and this is beam quality, this is not X-ray quality. Then we had filtration. We had two different types of filtration. What were they? Inherent and added filtration. What was inherent filtration? You can't take it away, right? So inherent filtration is what's inside of the tube, inside of the imaging system, really. So everything from the collimator housing up, we're going to call inherent filtration. And remember, inherent filtration does not stay the same over the life of the tube. How does it change? The tanning of the tube, so we get that lining of tungsten on the inside of the tube that increases that inherent filtration, right? And the other type is added filtration, and that's exam specific. You may have wedge filters and trough filters and things like that. And realistically, have y'all seen any kind of added filters? Any kind of compensating filters in clinicals? In a lot of ways, the digital processing has kind of replaced that. They still do have applications, but they're not as critical as what they were with screens and films. In order to get a good image of the foot from a toe to heel, whenever we're using screens and films, you had to use a wedge filter. You just don't have to do that anymore. So it's almost theoretical. It still does have an application, but it's almost theoretical. So also on the console, we had line voltage compensation. What did that do? Yeah, it made everything the same. It was like a surge protector. So that your KVP to your auto transformer was set so that you didn't have fluctuations in incoming line voltage. What did the auto transformer do?
Cut off exposure.
Cut off exposure?
Or no, the cut off. Oh, I'm thinking of AEC.
Yeah, you're thinking AEC. Auto transformer is our KVP adjustment, right? It works off of the transformer law, so the ratio of turns on the primary side versus turns on the secondary side, we could increase or decrease our KVP if we brought those contacts on the secondary side closer together. And what happened to our voltage? Went down, right? If we spread them out, went up. It's a single coil. Again, it works off transformer law. By adjusting the secondary contacts, we can increase or decrease potential to feed into the high voltage transformer. Do we have kilovoltage at this point? No, we don't. We're just adjusting voltage in anticipation of it becoming kilovoltage. So we got a lot of different words for the auto transformer. That's a rheostat, it's a variable resistor, it's our KVP adjustment. And what we have to make sure our KVP is going to be right is what we call a pre-reading KVP meter. A significant difference, not the significant difference, but a significant difference between an auto transformer and a high voltage transformer is a high voltage transformer has 2 coils and the ratio is set. So if we know what our voltage is coming out of an auto transformer, because of the transformer law and the high voltage transformer, we know exactly what our KVP is going to be once we run it through the high voltage transformer. And that's why we can use a pre-reading KVP meters, because we know if our voltage is right, our kilovoltage is going to be right. So KVP, the different names that we use for KVP, we've got 2 potential. What is potential? What's that?
Stored energy.
Yeah, stored up energy, so the ability to do work. So KVP, when we set our KVP, what we set is the relative positive and negative charges across the X-ray tube. So that when we make an exposure and we release those electrons, if we increase our KVP, what happens to the speed of those electrons? It goes up, right? We increase the KVP, the speed of the electrons go up. Now, once they become photons, what speed do you have there? Speed of light. It's all the same speed. So the difference in the behaviors of the photons exist at different energy levels. At high KVP, we have shorter wavelength, right? Shorter wavelength and higher frequency. But the electrons do change speed. The photons do not. So it's potential difference, it's electric potential, and we also call KVP quality. So it's adjusted at the auto transformer, it's created at the step-up transformer. We don't have KVP until we run it through the step-up transformer. So when KVP is adjusted, what changes in the pre-tube exposure? And that's the potential difference. That's a positive versus negative charge across the X-ray tube. So during exposure, that's the speed of the electrons. So if we increase KVP, we increase quality. If we increase KVP, we also increase quantity. We talked about that a minute ago. We tend to lock into quality, and we tend to lock into quantity being only controlled by mass, but that's not true. KVP affects quality as well. It's direct, but it's exponential, right? So how does it affect interactions? All interactions go down with the increase in KVP, but the photoelectric go down faster than the, photoelectric go down faster than the brems. So how does it affect the remnant beam? Again, exponentially increases in the remnant beam if we increase KVP. And how does that affect the image? This is where we're going to spend a lot of this semester being a little bit confused. It doesn't affect the image very much at all in a digital world. So we're gonna talk about how it affects the remnant beam and the exposure on the image receptor more so than what we're going to the actual image itself. Okay, so theoretically, if you increase your KVP by 15%, you increase your exposure and your contrast should go down. Okay, because you get more penetration through all different types of tissue. And it's still registry testable. But the confusion and the difficulty you're going to have in learning this is that in clinicals, it's not going to bear that out very well. Okay, so you get into clinicals and you start playing around with the machine, not on a patient, but you just start shooting things, which I really recommend that you do. Just find something, walk into a room, start blasting away on it. And it can be almost anything. Sharps container, it can be shoes, it can be whatever. If you happen to have a skull phantom, shoot it. But if you increase your KVP, then according to the theory in the textbook, what you should see is an increase in density and a decrease in contrast. And if you change your KVP by 15%, you take a look at both images, you're almost not going to see any changes at all. Okay, so you're going to have a hard time with that. We're going to talk about it in both contexts, but visually and clinically, it's gonna be difficult, okay? As part of the reason we go through this so many times is because in screens and films where it truly made a difference, it was hard enough, but now that the computer kind of fixes all that for you, it's even more difficult. Okay? So Kvp is adjusted at the auto transformer. Again, you got a change in tube potential. The kinetic energy of the electrons changes. You increase your Kvp, and the electrons go across the tube faster. If you decrease your Kvp, they go across the tube slower. So they're still fast, right? The slowest that they're going to travel across the tube is maybe a third of the speed of light, maybe a quarter of the speed of light. So they're going to be going really, really fast. We're talking about differences of a third to a quarter or a third to a half, right? So they're going to be going across the tube really fast regardless of what our Kvp is. So the more energy we have to lose, the higher the energy of the X-ray photons. Remember, we create X-rays in two different ways, right? We've got brims and we've got characteristic. So characteristic X-ray photons that we recognize always exist at the same energy level, and that is 69, right? It doesn't mean that we don't create characteristic in other energy levels, but that's the only one that we really recognize on the brim spectrum. But we do create a lot of characteristic X-ray photons in a lot of different energy levels. But what determines the energy level of the brim's photons? Basically, how the nucleus of the atom is going to influence the electron as it comes through that. So the more energy it loses, the higher the energy of the X-ray photon. So the electron comes through and loses all of its energy. We're going to have a very high energy X-ray photon, as opposed to if it loses very little of its energy, we're going to have a low energy X-ray photon. So as Kvp increases, we've got an increase in kinetic energy. We have more energy to lose, and therefore, with more energy to lose, we can create higher energy X-ray photons, right? So it's an exponential relationship to numbers. All interactions increase in numbers, but PE increases the least, and I think I just said that exactly backwards a minute ago. So as Kvp increases, because we get such an increase in X-ray photon numbers, what we get is an increase. It's a decrease before. I just scratched that. We get an increase in numbers, but PE increases less than what does scatter radiation. Okay. So higher energy, we get more penetration, higher percentage of scatter radiation. And that should, theoretically, since we get a higher percentage of scatter, higher percentage of penetration, that should give us lower contrast with higher exposure. Okay. So let's break this down. What controls your contrast? Okay, thickness. As tissue thickness increases, right? What do we get more of as tissue thickness increases? Scatter radiation, right? So scatter radiation, if we change the technical factor, it gives us a higher percentage of scatter radiation. Scatter radiation causes fog, and fog decreases contrast. Then you kind of get that walkthrough on how theoretically Kvp, increasing Kvp, decreases contrast because of the scatter radiation, right? But at the same time, even if we removed all those scattered photons, we're still going to lose contrast because with a higher Kvp, we're going to penetrate through a lot more tissues. All right, so let's stop on that. We've got a tissue type that either blocks all X-rays or transmits all X-rays. How many shades of gray will we have? We have two, right? It's perfectly clear and totally opaque, right? The image on the screen. So we only have two. But if I change my Kvp and I could penetrate a little bit of this one, and this one was still, block no X-rays at all, then what's the difference there? If I have totally opaque, and totally clear, then what's my contrast look like? Totally black, totally white, right? So if I increase my KVP and I penetrate this a little bit, now what does this one look like? It's more gray, right? So if it's more gray, does that bring those contrasts closer together? Yes. Okay, so even if we got rid of all the scatter radiation with the increase in KVP, we're still going to get a longer grayscale, less contrast, okay? All right, so chapter 7 and 8 are kind of lumped together. So what is KVP's effect on energy? Increases in KVP is what determines the peak energy. So you increase your KVP, then your peak energy goes up for the reasons we talked about before. You've got more to lose, and therefore your and creation of X-rays is all about loss of kinetic energy. So if we have more kinetic energy to lose, then we're going to have a higher peak energy. So increases in KVP increases the height of the bubble. Now we're talking about the Grimm spectrum, right? And so we're going to look at these, and then I'll raise the screens we talk about. So increases the height of the bubble, increases in KVP increase the peak energy, increases in KVP increase the average energy. KVP is what determines if we get a characteristic spectrum. So KVP has no effect on minimum energy. When we talked about that last semester, only one thing affects your peak energy, and that is KVP. Only one thing affects your minimum energy, and that is filtration. Exactly. Okay, so let's look at these other ones, and then we'll be pretty much out of time. But we'll pick up on it on Friday. We'll talk about the Grimm spectrum on Friday. So as KVP increases, patient exposure. Now, this is another thing you're going to have a tendency to struggle with on the tests. You're going to have to pay close attention to the test questions and what the test questions are asking you. As KVP increases in the X-ray tube, what increases? Talked about it just a minute ago. Speed of the photons, right? Speed of the electrons. Energy level of the photons, but what happens to the number of photons that we create? It increases exponentially, right? So if the number of photons increase exponentially in the X-ray tube, then emission from the X-ray tube, they're also going to be exponential. If you don't do anything else with your technique, you expose a patient with a higher KVP X-ray beam, what's going to happen to the exposure of the patient? We increased KVP, so we increased numbers exponentially, emission exponentially, and exposure to the patient increases exponentially, right? So we talk about high KVP as being a safer dose for the patient. You know, you get a pregnant patient that you're doing, God forbid you got to do an IVP on a pregnant patient. What kind of technique are you going to use? You're going to use high KVP, but you're going to use low mass, right? So KVP can be a better dose and a good dose to limit radiation dose to the patient as long as it comes with a reduction in mass. So you're going to have to pay attention to your test questions. They're going to come at you in a couple of different ways. Test question says something about you know, as you increase your KVP, what happens to patient dose? What's your answer there? It increases, right? Because it didn't say anything about reducing your mass, right? So if it just calls for an increase in KVP, then your answer, your patent answer, you know, just carry this all the way through the registry. If the only thing that it asks you for is a change in KVP, then your dose goes up with KVP increases and down with KVP decreases. But if it's asking you about KVP, if your KVP increases about 15%, your mass is reduced by factor 2, what happens to your patient dose? It's going to go down, right? Is your dose going to go down by factor 2? Well, no, because you increase your KVP by 15%. So your dose is gonna go down, but it's not gonna cut your dose in half. It's gonna be a better dose than a low KVP high mass dose, but it's not gonna cut your dose in half for the patient, okay? So as KVP is increased, patient exposure will increase dramatically if mass is not changed. So increase KVP, decrease mass, increase by 15% KVP, reduce your mass by a factor of 2, your dose goes down. It decreases if we have an increase in KVP and a decrease in mass. So what are the effects on image receptor exposure? Well, as you increase your KVP, you increase the numbers you create, you increase the numbers you emit, you increase the numbers that hit the patient. So naturally, what's going to happen to your image receptor if all you do is change KVP? Increase KVP, yeah, you get more penetration, and therefore you get more exposure to the image receptor. But if you increase your KVP by 15%, and decrease your mass by a factor of 2, you cut your mass in half, then what you should be doing, and that's truly your 15% rule, and what you're doing there is you're saving patient dose while maintaining image receptor exposure, okay? So where your dose to the patient goes down using that 15% rule, increase your KVP by 15%, reduce your mass by a factor of 2, your image receptor exposure should remain the same, okay? So now there's 3 different ways you got to pay attention to this. One is dose to the patient. KVP goes up, and that's all you do. Dose to the patient goes up. Right. And understand, I'm not going to talk about everything in the semester in both directions. I'm not going to say, okay, KVP goes up by 15%, you reduce your mass, and then I'm not going to turn around and say KVP goes, you reduce your KVP by 15%, you double your mass, then patient dose goes up, right? I'm not going to cover it both ways every single time. Just know that the opposite is always true. If KVP goes up and mass goes down, patient dose goes down. KVP goes down, mass goes up, patient dose goes up, right? So, again, 3 different things to look for. One is patient dose when KVP is changed, and that's the only thing that's changed. Right? KVP goes up, patient dose goes up. If we change KVP in our mass, we increase our KVP and decrease our mass, patient dose goes down. We increase our KVP and that's all we do, what happens to image receptor exposure? Goes up. We increase our KVP and we reduce our mass using the 15% rule. What happens, excuse me, what happens to image receptor exposure? It stays the same. Right. Right. All right. So we are out of time right there. Any questions on what we just did today? Oh, while I'm thinking about it, I did send an email out over the break. One of our clinical sites is willing to give the COVID vaccine at no cost to our students. You know, with the understanding that you know, they're going to take care of their employees first, but anything that they have left over, you know, essentially. And once they get everybody vaccinated who wants to be vaccinated, they can offer them to y'all. So show of hands, anybody interested in the COVID vaccine? And if you're not, that's fine. You know, I'm not trying to push you in either direction. I only had 2 responses over the break, so, you know, don't feel like you're alone in that. So, okay, all right. So I just got to pass those numbers on to the dean's office. Well, welcome back, and again, the slides should be over in the bookstore, and I'll have this posted here in just a little while.
I have a question.
Yep.
The videos that you said that you posted from last year, did you post them onto this semester's campus or last?
No, they're in, if you look, you may have to go to your dashboard and then go all the way to the bottom where it says all courses or all classes. and you may have to activate the class to get it to show in your dashboard.
Okay, yeah, they disappeared.
Well, yeah, they did. Did they disappear again? Because they disappeared and then I got them to reappear and then they're still not there.
Because
Really?
I tried to watch them on Monday.
Really? Okay, I'll have to go back in and take a look at them again. All right. Okay. That's good to know. All right, I'll take a
Well,
look.
they're not there online. I don't know if
Any,
they're-
has anybody looked this week?
I've
Well, I
been
was-
trying to watch them like the whole break, and I wasn't able to, and whenever they said it was up, you said it came up about like,
I was able to watch it last Tuesday.
Last
they're
week.
up there.
Are you showing them? Okay. Okay, so that's, 0091, is that right? Let me, the train will be down here, so, could somebody look outside and make sure Trina's not, just kind of sitting out there waiting for us? Because she can come in and start getting ready.
0090.
0090,
Yeah.
okay. And, she's not out there? Oh, no? I don't know why that one over there won't work.
I see where it says all courses now, and it is under the all courses.
It is?
Yeah,
Okay,
it's just
okay,
not under the
okay. Okay.
regular
All right.
courses.
I'm gonna raise those and hopefully that other one. Hopefully it'll work for Trina. Are you able to see them?
Yes.
You are able to see
No,
them?
you just have to go to the all courses, and it's like past semesters or whatever.
Yeah, yeah, and if you check the star so that it's highlighted, it should show up in your dashboard.
Oh, okay.